Before we start talking about the lesson, I want to bring up some interesting points about these properties of logarithms. So here's the page of the properties done correctly. So we often say we're condensing or expanding because if you notice, we only wrote the word log once on one side, but we wrote it twice on the other side. So one log could become 2, or 2 logs could become 1. That's true here as well. And although the last one isn't really a condensation, there is something specific it's saying. It's saying that inside, or the argument of the logarithm, the exponent of that argument gets to come out to the front. Well, there's some misleading properties or things that aren't really properties. And we're going to look at those right now before we jump into the lesson. So here's one. In green is the actual property, in red is a fake one. So we're not saying that you have a product of logs. You're not multiplying logs together and just turning that into addition. It's a multiplication inside of a log. The argument, right here's the argument. That part of it is multiplication and then becomes an addition of logs. And similar to that, it's a division inside the argument, not a division of logs. And lastly, it's the power inside the argument that gets to come out front. We're never talking about an exponent of the entire logarithm. So with those things in mind, let's begin the lesson. We're going to start by going over the jump start. We're going to skip that and go right to the launch. Abe and Mary are feeling good about their log rules and bragging about their mathematical prowess to all their friends when this exchange occurs. Stephen says, I guess you think you're pretty smart because you figured out some log rules, but I want to know what they're good for. And Abe says, well, we've seen a lot of times when equivalent expressions are handy. Sometimes when you write an expression with a variable in it in a different way, it means something different. What are some examples from your previous experience where equivalent expressions were useful? Well, back in integrated 1, you may have looked at a line being y equals mx plus b, and you may have translated a paragraph into a linear expression ax plus by equals c. Or maybe last year in integrated 2, you looked at quadratics in standard form, and then maybe you looked at them in a slightly different form, which we call graphing form. Some forms are easier for graphing, some forms are easier for using to solve equations or identifying features. Now, Mary says, I was thinking about the log logic task where we were trying to estimate and order certain log values. I was wondering if we could use our log rules to take values we know and use them to find values we don't. For instance, let's say you want to calculate log base 2 of 6. If you know what log base 2 of 2 and log base 2 of 3 are, then you can use the product rule, change that multiplication of 2 times 3 into an addition of the logs. And Stephen says, that's great. Everyone knows, hopefully they do, that log base 2 of 2 is 1, but what's log base 2 of 3? And on the next page, Abe says, oh, I saw this somewhere. Log base 2 of 3 is 1.585. So Mary's idea really works. And you say, okay, based on what you know about logarithms, Explain why 2.585 is a reasonable value for log base 2 of 6. Okay, so here's the work that they did over here to come up with a number. Remember that 2 to the second is 4, but 2 to the third is 8. And so in between those must be log base 2 of 6. So it's going to be 2 point something because we're here between the second power and the third power. And there it is. Steven says, oh, I've got one. I can figure out log base 2 of 5 like this. And here's his work. Can Stephen and Mary both be correct? Who's right, who's wrong, and why? Well, Stephen messed up. He changed an addition to an addition. In effect, he kind of distributed the log. And in our last lesson, we saw you can't do that. So Stephen is wrong, and he used an illegal maneuver there. You can't distribute a log. You can't distribute a function. You can't distribute, I spelled that wrong. Distribute, anyway, you got the idea. A function. Now you can try applying the logarithm rules yourself. Use the values that are given and the ones that you know by definition, like log base 2 of 2 is 1, to figure out each of the following rules. Explain what you did in the space below each problem. Okay, so here's what we have to work with, plus some very basic rules and the 3 rules of logarithms. And here's the puzzle. Log base 2 of 9 on number 4. Well, you can write that as log base 2 of 3 squared. And then you can bring the 2 out in front. It's 2 log base 2 of 3. But up here, we know that log base 2 of 3 is 1.585. And so if we multiply that out, we're going to get, let's see, it's about 3.17. Okay, log base 2 of 10. So think about how we can use 10. Well, they do give us log base 2 of 5, and we know log base 2 of 2. So log base 2 of 10 is 2 times 5. That changes to an addition of log base 2 of 2 plus log base 2 of 5. Log base 2 of 2 is 1. Log base 2 of 5 is 2.322. So add those together, 3.322. And finally, 12. On problem number 6, log base 2 of 12. That could be 6 times 2. But how about we do 3 times 4, and then we can figure out log base 2 of 4. So log base 2 of 3 times 4 is log base 2 of 3 plus log base 2 of 4. Log base 2 of 3 is given as 1.585, and log base 2 of 4, 2 to what power is 4 is 2, so this is 3.585. So it's just kind of a game, trying to figure out how you can break down the numbers. And there is some more practice here we're going to need to skip this for now and go to this last set here. Sometimes thinking about equivalent expressions with logarithms can get tricky. Consider each of the following expressions and decide if they are always true for the numbers in the domain of the logarithmic function, sometimes true or never true. Explain your answers. If you answer sometimes true, describe the conditions that must be in place to make the statement true. Okay, so basically what we want to do is we want to find the ones that are the real properties, and those are always true. So number 11 turns a subtraction into a division. This is always true. Number 12 takes two subtractions, puts them in the denominator. So that's good. However, on 11 and 12, there's something else that has to be true. You notice how x is in the denominator? Well, you can't divide by 0, so you also need to add x has got to be greater than 0. Actually, not greater than 0. Yeah, greater than 0, because on this one, we don't want the log to get a negative number. That would be out of the domain. But for this one, since it squares it, we just need x to not be equal to 0. And let's see, number 13, this is not a real property. So it could sometimes be true. Let's cut away to Desmos, and I'll show you when that's true. Okay, back to 14. This is a real property. This is always true. No restrictions. Except, of course, that x has got to be positive. You can't be putting a negative into a log. Here I am over on Desmos, and this is problem number 14. I put the left side of the equation equal to y. I put the right side of the equation equal to y. If you look at where do these two cross each other, they really only cross each other in one spot. You can see it's right there, so it's sometimes. 15 is also sometimes true. You could solve that with Desmos. 16 is a real property. It's always true. Of course, x would have to be greater than 0. And 17 is a fake property. And if you try to solve that with Desmos, you don't even get a solution. This one would be never true. Okay, so a few takeaways then. Strategies for working with logarithmic expressions using properties of logs. As always, look for powers of the base. Like, for example, when we did log base 2 of 4. And don't try to apply a log rule to addition or subtraction in the argument. So watch out for something like this, because that's not going to give you the log of A plus the log of B. Oops. Let's try that again. Log of B. And then finally, if multiplication or division is not inside the argument, then the product and quotient rules don't apply. So if you have, so watch out for this one too. If you do the log of A divided by the log of B, that is not the log of A minus the log of B. That's one of those misleading properties. Okay, we'll see you next time.